So we have done a little bit with area under a curve so far. We started in the last chapter, and remember we started back with the very basic idea that if we were trying to find the area under a curve, we could make all those rectangles and add up the areas of all the rectangles. And then from there we kind of extended that idea, and we talked about left hand, right hand, and midpoint sums, and then eventually we said that area under the curve was the same thing as what? The antiderivative. So we start out with a very annoying process to get there, and then ultimately we were able to realize this is just the antiderivative, and we could work it that way. But this section, I want to talk about the area between two curves. So everything we've done so far is just between the x-axis and the curve, but what if I had two different curves and I wanted to get their areas? Well, so if we think about it different ways, we could say, well, we could go back and do the original idea where we made up all these rectangles and added up the areas of the rectangles. And we know that if we wanted that to be accurate, we had to do the limit as the number of rectangles went to infinity of the sum from 1 to n. And to get the area between them, you'd have to do the top one minus the bottom one. Times the width of the rectangles, because the area is just length times width. But really, this is just the definition of an integral. And if we think about this, we know if, for instance, let's make it two curves above the x-axis for a second. I think that might be a little bit easier. So if I wanted the area between these curves, okay, if you did the integral of the top one, you would get this entire thing, right? And if I did the integral of the bottom curve, we would get this. So how would you get the area between the two? Subtract them. So that's really all we have to do. We don't have to do the rectangles and add up all the areas and that whole bit. We can just integrate from A to B, or starting to stopping, the top curve minus the bottom curve. And so that is all we are going to be doing here. More integrals, so all these integration techniques that we've been using. We just have to set it up for the top minus the bottom. So a picture will be helpful to figure out which curve is on top. So let's look at an example. I want the area of the region bounded above by y equals e to the x, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. A picture is helpful on these, but you don't have to have a super elaborate picture. We're going from x equals 0 to x equals 1, right? So a lot of times if I'm trying to make my picture accurate, I'll plug those into my equation. So e to the 0, anything to the 0 power is 1. E to the first, that would just be e, which is like 2.7. So when I plug in a 1, I get out like a 2.7. So there's my top curve. Y equals x. So if you plug in your points, if you plug in 0, you get out 0. If you plug in 1, you get out 1. So we are just trying to find this area between those two things. So most of the time, like on test or quiz, if I'm asking you to find these areas, I will ask you to draw a picture and give you a point for drawing that picture. But the whole purpose of it is really just so you're paying attention to which curve is on top. What do you think would happen if you did the wrong one first? You'll get a negative. And so you should catch that at the end, because should area be negative? No. So if I did this and got -2, I know I flipped it, and so the easy way, instead of going back and reworking your whole problem, would be to throw a negative in front of your integral and make your answer positive. So if you set it up wrong, you should know at the end, because your answer is negative, and to fix it, you just tell me the positive. Okay, you don't have to rework the whole problem. So we are going to integrate. We are starting when x equals 0 and ending when x equals 1. And we do the top curve minus the bottom curve. So my top curve is e to the x. My bottom curve is x dx. I know there might be a little bit of confusion because these equations had y's in them, and we will look at things that have both x's and y's. You have to realize all of your variables have to match. So 0 and 1, those are x values. So these can only have x's. And if everything else is x, that should be a dx. Tomorrow we will look at some where we integrate in terms of y, and I'll show you why we might do that. But you just have to make sure the numbers on your integral, the variables you use throughout are all the same. All of these are x's. And then this is something we should be able to integrate. What is the antiderivative of e to the x? E to the x. Minus, what is the antiderivative of x? So if I plug in 1, I get e to the first, which is just e. Minus 1/2 times 1 is 1/2. Minus, if you plug in a 0, e to the 0 is 1, minus 0. So we get e minus 3/2, or e minus 1.5. Any questions on that one? The next slide, like I already said, it's a good idea to have a picture so we know what's top and bottom. So let's look at this. I want the area enclosed by the parabolas y equals x squared and y equals 2x minus x squared. First of all, I didn't tell you when to start and stop on this one. When I say enclosed, that means these curves meet somewhere, and I want the area between them. So what we could do is figure out where these things meet. So they're both equal to y. Let's set them equal to each other, so that I know where I'm going to start and stop. And I'll use that to help me draw my picture. So if I'm going to set this equal to 0, I would add over my x squared, subtract my 2x. Then what could we do? Factor, take out 2x, this is x minus 1. So if you set each of those equal to 0, you get x to be 0 and 1. So we are starting at 0, ending at 1 here. And I'm sorry, I probably should have put in some blank slides so you guys will have more workspace on this. I apologize. Okay, so to try to draw a picture, let's see. We know a parabola is curved. If we put in 0, 0 squared is 0. You put in a 1, 1 squared is 1. So we have just this piece of a parabola. This one, if we put in 0, we get 0. If we put in 1, we get 1. Did that really show us which one was on top? No. Let's try something in the middle. If I put in 1/2. 1/2 squared is 1/4. Okay, so that first parabola, let me make sure. If I put in 1/2, we get out 1/4. So if I put in 1/2 here, 2 times 1/2 would be 1, minus 1/2 squared is 1/4. So 1 minus 1/4 is 3/4. So now we can see we're finding this area, and which one was on top? 2x minus x. So we're integrating. These are x values from x equals 0 to x equals 1. So we do the top, 2x minus x squared, minus the bottom. So 2x minus x squared minus x squared would be minus 2x squared. So antiderivative of 2x. X squared minus antiderivative of 2x squared. 2/3 x cubed. We plug in a 1 squared is 1. 2/3 times 1 is 2/3. Within 0, you get 0 minus 0. So 1, that's like 3/3 minus 2/3. So we get 1/3. So I'm asking for the area bounded by the lines y equals x equals 2, and y equals 1/x squared. Okay. So I have really 3 pieces here. What's x equals 2? That's a vertical line. So this is my x equals 2. So that's going to be our stopping point. Y equals x, we know that's just a line. You put in 0, you get out 0. If you put in 1, you get 1. If you put in 2, you get 2. What would I do about the 1/x squared? Can you put in 0? No. What if you put in 1? 1/1 squared is 1. If you put in 2, 1/2 squared would be 1/4. And we know this is just like a vertical asymptote. So it looks like this. So I kind of got my graph just by plugging in some points. And we were lucky we saw where these two curves meet just by that. You could also set them equal to each other if you wanted to do it that way. 1/x squared equals x. So if you multiply, you get x cubed equals 1. Cube root of 1 is 1. So we see that they meet when x equals 1. So when I integrate, where will I start and stop? Where do we start? At 1. Where do we end? At 2. Top minus the bottom. What's my top curve? X minus the bottom curve. For the purposes of doing the antiderivative, if you would like, 1 over x squared, you could rewrite that as x to the negative 2. So the antiderivative of x squared. All right, antiderivative of x to the negative 2. So if you add 1 to the power, negative 2 plus 1 is negative 1. So we would have to have a negative 1 in front, so it would just be plus x to the negative 1. So if we plug in 2. 2 squared is 4, times a half is 2, plus 2 to the negative 1, so 1 over 2. Minus, if we put in a 1, 1 squared is 1, times a half is 1 half. 1 to the negative 1, so 1 over 1 is 1. And we get 1 for the final answer. What questions do you guys have for me so far? Do you understand how I'm finding the limits, where we start and stop, and which one I put first? So. Just need more problems, you think?
Yeah.
I think I want to skip this one for a minute. This, I already kind of mentioned this, that area has to be positive. So you could really subtract, if you got confused and you couldn't figure out which one was on top, technically it wouldn't matter, just if you get a negative at the end, the area is the absolute value, so the area would have to be positive. So we can always fix it like that if we make a mistake. Let's do a trig function. Life isn't complete without some trig for today. I want the area between the curves y equals sine x, y equals cosine x, 0, and pi over 2. So remember back at the very beginning, we graphed our trig functions. This is 0, this is pi over 2. Sine of 0 is 0. What's the sine of pi over 2, or the sine of 90 degrees? 1. So sine from 0 to pi over 2 looks like this. Cosine. What is the cosine of 0? 1. And the cosine of 90, 0. So this one, we have a little issue. Is the same function always on top? No. So we have to break this up. Where do these two things meet? My picture is not completely accurate. When are sine and cosine the same? At 45 degrees, sine is radical 2 over 2 and cosine is radical 2 over 2. So that's my pi over 4. So we're going to have to do this one over two separate pieces. We're going to go 0 to pi over 4. Then we're going to go from pi over 4 to pi over 2. From 0 to pi over 4, which one was on top? Cosine. So that's cosine x minus the bottom would be the sine x. From pi over 4 to pi over 2, then sine was on top, so we'll have to do sine x minus Now we integrate. What's the antiderivative of cosine? Sine minus. What's the antiderivative of sine? Negative cosine, so that becomes plus cosine of x. Antiderivative of sine is negative cosine. Antiderivative of cosine is so now we evaluate this. Okay. Sine of pi over 4, that's like the sine of 45 degrees, so radical 2 over 2. Cosine of 45 is radical 2 over 2. Minus the sine of 0 is 0, cosine of 0 is 1. Negative cosine of pi over 2. So the cosine of 90 is 0. So the opposite of 0 is just 0. Sine of pi over 2 is 1. Cosine of pi over 4 is radical 2 over 2. Sine pi over 4 is radical 2 over 2. So radical 2 over 2 plus radical 2 over 2 is just radical 2 minus 1 plus negative 1. If I distribute this negative, and that's just a positive radical 2. So 1 radical 2 and 1 radical 2 is 2 radical 2. Negative 1 plus negative 1 is negative 2. I'm stopping here today. Tomorrow we're going to finish the notes, so if you're not here, there will be a video. I want you to go ahead and start trying some of these. I'm only giving you 3 problems today, and 2 of them, the pictures are already drawn, so there's only 1 problem where you have to do everything. If you're going to be gone, the other problems for this section